Hello students, welcome to my channel NCERT Unplugged, and in this video I'll explain you article number 5.2.3, the dipole in a uniform magnetic field. Okay, so in the first chapter, that is electric charge and fields, we have seen that when we place a electric dipole in a uniform electric field, that experience a torque. Okay, and the torque try to rotate the dipole in the direction of the electric field. Okay, we have seen that. Okay, and the expression for that torque in that case was, because we know torque is a vector quantity, and it was P cross E. Okay, you can see those lecture and you will find this expression. Okay, so similar to that case, when a magnetic dipole is placed in a magnetic field, then external magnetic field, then what will happen? This magnetic field will exert torque on this magnetic dipole. Okay, and the torque is given by M cross B, where M is the magnetic dipole moment of the magnetic dipole and B is the external magnetic field. Okay, so let's look more in this paragraph and study about it. Okay, so the pattern of iron filings, that is the magnetic field lines, give us an approximate idea of the magnetic field B. Okay, so as we have seen in the previous video, that we have seen that iron filing arrange themselves in certain pattern, and with that help of pattern we can find out how much is the, how we can get an idea about the field. Okay, so now how is the field there and how much is the field? We know when the magnetic field lines are close to each other, that there the field strength is more. Okay, in that particular region. Now we may have at times be required to determine the magnitude of B accurately. This is done by placing a small compass needle of known magnetic moment M and moment of inertia I, and allowing it to oscillate in the magnetic field. Okay, so when we have to find the magnetic field magnitude of magnetic field accurately. So how do we do that? We place a magnetic compass or magnetic compass needle in a magnetic field. Okay, whose magnitude we have to find. Okay, and this magnetic compass magnetic moment will be known to us. Okay, and the moment of inertia of this magnetic field will be also be known to us. Moment of inertia we have seen in class 11. Okay, it is analogous to mass in case of rotational motion. Okay, so we'll let the magnetic compass needle rotate with having magnetic moment M and moment of inertia I, rotate, oscillate in the magnetic field. There will be torque acting on this magnetic compass. Okay, so now this arrangement is shown in figure 5.4b. okay, so if you see 5.4b, the diagram, I have to search, wait for a second. 5.4b is here. Okay, so you see there's a magnetic compass here, and it is kept in a magnetic field. It is we have let it free to oscillate in this magnetic field. Okay, now so the torque will be how much? So this will be torque M cross B. Okay, now in magnitude this will be, because M cross B is what, MB sine theta. Magnitude wise this will be MB sine theta, where theta is the angle between M and B. Okay, and tau is the restoring torque. Therefore in equilibrium, deflecting torque will be equal to restoring torque. Okay, so now you know what is the formula for torque in terms of moment of inertia and angular acceleration. Torque is equal to moment of inertia times angular acceleration. Okay, in rotation motion, in linear motion, this is analogous to force is equal to mass times acceleration. Okay, for this in rotational motion, this is torque is equal to moment of inertia times angular acceleration. And what is angular acceleration? This is d2 theta by upon dt square. Okay, you have studied this in class 11. Okay, and now this is equal to deflecting torque is equal to restoring torque. Okay, that is mb sine theta. We have put a minus sign because this two torque will be in opposite to deflecting torque. Restoring torque will be opposite to negative sign with mb sin theta implies that restoring torque is in opposition to deflecting torque. Okay, now for small value of theta in radians, we approximate sin theta is equal to approximately equal to theta. Okay, so we know for theta smaller angles sin theta is approximately equal to, we can take sin theta as equal to theta. Okay, so we have taken that. So I d square t theta upon dt square is equal to mb theta and not sin theta. Okay, we have taken sin theta for small value of theta. And now what we do, we take this I in the denominator, so it becomes d2 theta upon dt square is equal to minus mb upon I dot theta times theta. Okay, now this represent a simple harmonic motion. You know, equation of a simple harmonic motion, acceleration is equal to minus omega square times x. Okay, where omega is what? Angular frequency. Okay, here it is alpha. Okay, angular acceleration to minus omega square times theta. Okay, and now this is also alpha. Okay, acceleration, angular acceleration. Okay, and if you compare this by this, you'll see that omega square is equal to mb upon I. So omega square is equal to mb upon I. Okay, now omega is what? mb upon I root. Okay, and now you know omega is angular frequency is 2 pi f. Okay, 2 pi times frequency, or you can say 2 pi upon capital T, that is the time period. Okay, so time period will be what? Time period will be what? From this, you know, omega is equal to 2 pi upon T, capital T, so capital T is 2 pi upon omega. And if I put the value of omega, I'll get what? 2 pi. Omega was this was what we are getting, I upon 2 mb upon I. So this, because omega is in denominator, so it will be root of I upon mb. Okay, and now from this, when I square this, okay, I'll get t square here. Okay, I'll get 2 square is equal to 4 pi square and I upon mb. So on rearranging, what I get, b is equal to 4 pi square I upon mt square. 4 and pi is constant. Moment of inertia of that needle is known to us. Magnetic moment, dipole moment of that is also known to us. Okay, and time period will be, we can calculate. Okay, so this way we can calculate the magnetic field of the required magnetic field. Okay, an expression for magnetic potential energy can also be obtained lines like similar to electricity potential energy. Okay, if you remember from second chapter, the expression for potential energy of an electric dipole placed in a magnetic electric field was U is equal to minus P dot E. Similar here, it can be obtained as U is equal to minus MB. In place of magnetic electric dipole, there will be magnetic dipole moment, and electric field there will be magnetic field. That is a dot product of MB. Okay, or you can say U is equal to minus MB cos theta. How did we obtain that? If you remember what we did, the work done in moving rotating a dipole from theta 1 angle to theta 2 angle, okay, a small angle d theta, was work done was tau d theta for small work done. This will be small work done. For total work done from theta, rotating the dipole from theta 1 to theta 2, this will be work done will be integration of t d theta from theta 1 to theta 2. And you know w is equal to what? W is simply tau is what? We'll put the value of tau, that is mb sin theta. Okay, mb sin theta. Okay, this is in integration theta 1 to theta 2. So now we obtain w is equal to mb cos theta and minus cos theta, because sin theta integration is minus cos theta and theta 2 limits are this. Okay, and after the putting the value, the limits, we'll get mb minus cos theta 2, and then what we get, plus, okay, plus cos theta 1. Okay, so what we get, W is equal to mb cos theta 1 minus cos theta 2. Okay, so now we'll take the initial position as theta 1 is equal to 90 degree. We'll take the potential energy at 90 degree of the dipole as 0. Okay, because we know what actually matters is the potential energy difference. We have studied this in detail in chapter number 2. Okay, so we'll take the theta 1 is equal to 90 degree. This will be the initial position where potential energy will be 0, and the other angle theta 2 will take as theta. So what we get, we'll obtain W is equal to, and W is what work done is the potential energy of the dipole. Um is equal to W is equal to minus mb, because cos 90 is 0 and theta 2 is theta. Okay, so mb cos theta. So this is how I obtain the expression of potential energy of a dipole present magnetic field. So now we have emphasized in chapter 2 that the zero of potential energy can be fixed at one's convenience. Taking the constant of integration to be 0 means fixing the zero of the potential energy is equal to 90. Okay, so we have taken the zero of potential energy of the dipole at theta is equal to 90. When then it is perpendicular to the field, you know the difference of potential energy that really matter. We can take any position as 0. Okay, and with respect to that, the potential energy difference will be matter. Okay, so equation 5.6 shows the potential energy is minimum at theta is equal to 0. Okay, when I put theta is equal to 0 here, what I get, U is equal to minus mb. This is the least. When what that means, this is the dipole is like this. Okay, dipole is like this. Okay, here when theta is equal to 0 degree. Okay, theta is equal to the magnetic moment and the magnetic field are in the same direction, and in that case what happens, in that case the dipole is the most stable. Okay, while when I take theta is equal to 180 degree, in this case south, this will be north, this will be south, this will be north. Okay, and when I take north to be here and south to be here, so dipole moment will be here. Okay, in the opposite direction, theta is equal to 180 degree. This will be most unstable position because there is potential is positive, here it is negative. Okay, so this is all for this paragraph. I hope I was able to make you clear this paragraph. Okay, you can give me your feedback in the comment section. Like this video if you understand the video, and share with your friends. Do subscribe to the channel and hit the bell icon. Thanks for watching.